Over the past several weeks, we've focused on the pattern-oriented and object-oriented design and implementation of our expression tree processing app case study. However, there are other ways of designing software. So what we're going to do here to give you a different perspective is talk about algorithmic decomposition of our expression tree processing app case study. The first part of this lesson, we'll talk about how to do algorithmic decomposition of the expression tree processing app, and then we'll talk about the pros and cons of this approach in later parts of the lesson. Algorithmic decomposition is a historically popular design method that structures the software based on the actions performed by the system. If you take a look at the link at the bottom of this page, you'll get a chance to learn more about algorithmic decomposition and compare and contrast it with object-oriented approaches. The way that algorithmic decomposition works is it iteratively and recursively decomposes general actions in an algorithm into more specific actions using something called stepwise refinement. The design components that come from an algorithmic decomposition often correspond to the processing steps in an execution sequence. People sometimes like to use a recipe as an example of algorithmic decomposition. If you want to make something like a turkey burger, then you start by getting the ingredients and you mash up the meat and you heat the oven and you put seasoning packets in there and you put in the various accoutrements like beans and corn and tomatoes and so on. You put everything into the container, into your pan that you're going to use to cook, or your bowl you're going to use to cook, and you go ahead and cook it in the oven. So it's very much about the steps that are involved. These steps in an algorithmic decomposition software program, as opposed to a recipe, are typically implemented by functions. And oftentimes these functions, historically at least, have been implemented using second-generation programming languages like Fortran or C or Pascal. We'll explore the algorithmic decomposition and the decomposition of the algorithm into the functions here in a very short time. So let's take a look at how you might implement an expression tree using algorithmic decomposition using C. So C, of course, is a very popular programming language. In fact, arguably at the moment, it's the world's most popular programming language again. C and Java tend to go back and forth, trading off as to which one's going to be the most popular, according to the TOBE index that measures various things like number of references to the languages in social media, job postings on places like monster.com and glassdoor.com and so on. So we're going to use C to demonstrate how we would develop the main data structure for the expression tree processing app using an algorithmic design. So in this case, we're going to have a struct called a tree node, which is a C construct. Of course, it also appears in C++ as well by backward compatibility. And inside of this struct, we're going to define an enum type tag that will keep track of the different types of nodes in an expression tree. So we're going to have number nodes, unary nodes, and binary nodes. So those are the three different types of enumeration literals or enumerals that we're going to have as part of our type tag enum. We're also going to keep track of a reference count that can be used in case we want to share representations in some ways. You can reference count stuff to avoid having to have multiple copies if you don't need them. The next thing we're going to do is we're going to make a union that will have different contents depending on whether or not we are a num node or a unary or a binary node. So as you're probably aware, a union is basically kind of like a struct where all the fields or all the data members all have offset 0. They all start at the same location. So you can have different views of the contents in a union. So one of the pieces in the union could be a number, which would correspond to the num type tag. And the other element that would be in the union would be a character array, which would contain various numerical operators like plus, minus, times, divides, and so on, depending on whether we have a unary or a binary node. We then go ahead and define yet another union, which is going to be used to keep track of the number of children we have in case this is a so-called interior node in our expression tree. So remember that expression trees have leaf nodes, which are numbers, and then interior nodes, which are operators, things like plus and minus. So keep in mind we have a couple different types of nodes. We have unary nodes, which have basically a recursive reference or a pointer to a struct node, and that's called unary underscore. And then we also have binary nodes, which are going to have a left and a right child. And those would be things like binary multiplication, binary division, and so on. The unary node would be used for things like unary negation. Well, if you were to take a look at this and to try to use UML to describe this particular data structure, you'd have a very strange diagram here. I've shown you what this looks like. A tree node is a node that has either 0, 1, or 2 references back to itself, depending on whether it's a number, a binary node, or a unary node. And you can also see that if you were to look at the representation in memory of a tree node, it would contain a type tag, a reference count called use, then the union that either has the op or the num, and then the union that either has the unary or the binary pointers. So one of the consequences, as we'll see later when we go and evaluate this, is that even for the leaf nodes, which take up over half the tree, you're paying the price for all the various elements that you're going to have. And this is a very common way of designing things in a language like C. The other thing that's very common when you design software that looks like this is you'd probably use a switch statement and a recursive function to build and evaluate the expression tree. So this particular function is showing how to print the tree, and it's passed a pointer to a tree node and a file pointer. And what it's going to do, of course, because this is using kind of the classic C way of doing things, is it switches on the type tag using a switch statement. And then based on whatever tag it is, it carries out the right behaviors using the various cases that are listed below. So if it's a num type tag, we go ahead and we print the contents as a number using fprintf. If it's a unary tag, then we go ahead and print an open paren, make a recursive call to go down the unary branch to print that out, whatever that happens to point to, and then we print the closing right paren. If it's a binary node, we print the opening paren, then we make a recursive call going down the left-hand side of the tree. We then print the operator, and then we go ahead and recurse down the right-hand side of the tree, and then finally go ahead and print out the closing right paren. So you can see here that this is kind of classic recursive traversal of a binary tree, and using switch statements and case labels to figure out what to do.